Are you a high school chemistry teacher interested in implementing storylines into your chemistry curriculum? Then this video is for you. Here, I'm going to share the second lesson of the chemical bonding storyline. If you are interested in hearing about the first lesson, then click on the link above, which will take you right to it. Briefly, what's a storyline? It's like a red thread that connects the various activities to one another. The chemical bonding storyline encompasses 12 lessons. The second lesson focuses on, do only chemical reactions get colder? Here you see an image of the student handout, highlighted with images taken from my own classroom. To give you an idea where we are in this sequence, the first lesson was what happens when these substances are mixed together. During that first lesson, I covered 5 chemistry concepts. It took me 3 weeks to cover it. And just so you know, at my school, 5 lessons take about 50 minutes per lesson per week. I covered the following 5 concepts in those lessons, including this storyline, lesson 1. But in this video, I'm focusing on the second lesson, do only chemical reactions get colder? While I was focusing on this second lesson, I was also teaching a total of 12 chemistry concepts. Taken together, lesson 2 and these 12 concepts took me 4 weeks. Again, 5 lessons per week. What were these 12 concepts? Many of them related to the atom. But concept number 1.9, 1 for the unit, 0.9, the number within that unit. How can you tell whether solvation is a physical or chemical change? That's the focus of this second storyline lesson. Besides concepts 1.6 all the way to 1.13, I also started teaching the second unit, which is nuclear chemistry. Of the 4 concepts I covered, 2.1 through 2.4, number 2.3 focuses on why do salt solutions conduct electricity, which is related to the second lesson. Here you're seeing the front page of the key. If you're interested in the lesson itself, as well as the teacher key, check the description in the video below. This is the first lesson slide that the students see, where I introduce the second lesson, do only chemical reactions get colder? And again, this is part of the chemical bonding storyline, why do some things get colder or hotter when they react? So you see here 2 of my students actually carrying out the procedure. And if you focus on the thermometer, you can tell that the temperature is slowly dropping from roughly room temp, 22 or so degrees, down to about 15.2 degrees Celsius. But in order to answer the question whether this solvation of potassium chloride in water is a chemical or a physical change, I had my students boil away all the water so that they're left with the salt that they started with. And you can decide whether you want to speed up this reaction on a hot plate or you want to put all the beakers by the vent if you have time to spare. One thing that they noticed is that they pretty much got the same amount of solute back compared to what they started with. So as my students are thinking about the question, is salt solvation a chemical or a physical change, we have to keep the following in mind. A chemical change is any process that either creates a chemical structure, destroys a chemical structure, or converts one chemical structure to a different chemical structure. A physical change is anything else. I should note that I did not create this particular slide. This slide comes from the following website. This website does a really nice job of delineating between chemical versus physical reactions. And this particular simulation, I highly recommend having your students go to this, really delves deep into that. So again, lesson 2, where they are dissolving potassium chloride in water, once they've done that, they're going to do a bunch of tests with that. Here you're seeing one of my students scraping out all those white crystals and doing a conductivity test. Control shows deionized water does not conduct, nor does solid potassium chloride. Using a more quantitative conductivity meter shows 24 parts per million. For the solid potassium chloride, 0. But after redissolving the potassium chloride that was originally retrieved, we can see the conductivity is quite high. With our quantitative meter, we're seeing 2,360 parts per million. Next up was a flame test. Do we get a similar color back? Water is the control. Testing the solution gives us a very characteristic pinkish color indicative of potassium. Doing the same flame test with the original potassium chloride salt shows you a similar pinkish color. To really understand what's happening at the particle level, I had my students use the following models. They are magnetic water molecules like these, and magnetic models of potassium and chloride ions like these. On the left you see liquid water, on the right you see that very organized crystal lattice of potassium chloride. So since my students observed a slight temperature drop upon solvation of potassium chloride in water, what was that thermal energy used for? The left image highlights that the connections between the water molecules need to be broken. On the right, it's emphasized that the connections between the potassium and chloride ions also need to be broken. Perhaps not all, but you get the idea. The breaking of these connections requires thermal energy. Students are not yet ready to understand this concept, the fact that water and salt ions love to mix with one another. Second law of thermodynamics, increase in entropy. And upon the making of these new connections, ion dipole forces, energy is released. But I'm not emphasizing that yet in this second lesson. Of course, if students add more salt than the water itself can handle, then some of the solute will sink to the bottom. So besides doing the modeling with the magnets, I also had my students draw all this on magnetic whiteboards, using both magnets and markers. So is the solvation of a salt in water a physical or a chemical change? Well, chemical reaction, salt bonds are broken. A physical reaction, there are some connections between water molecules that had to be broken as well. But the water molecule itself remained intact. So that suggests that the solvation of a salt in water may represent both a chemical and a physical reaction. Here I'm showcasing a second lab group with a very similar looking model, highlighting that conductivity can happen when ions, which is synonymous with electrolytes, are actually moving. After my students completed their modeling, both with the magnets and the whiteboard with some magnets, we actually had a discussion about what should be included in the model. What are the important scientific terms? What evidence must we account for? What is also helpful is that these storyline lessons really emphasize driving question boards. What you're seeing here are the 6 questions that my students came up with at the end of lesson 1. We are processing now these questions as part of lesson 2 to see what questions are remaining, what new questions are coming up that we will take with us for lesson 3. A sneak peek to lesson 3 is where students, after working in groups and discussing things as a class, are able to individually create a digital model of the solvation of potassium chloride in water. This chemical bonding storyline follows the next-gen science standards as well as the New York State science learning standards when it comes to both matter and, of course, energy. If you are interested in all the lessons associated with this storyline, go to the video description below. It'll take you to Astrid's landing page. And in exchange for your email, you will get the link to the following Google Doc with access to all these resources. Thank you very much for watching. Bedankt voor het kijken. See you in the next video. Tot ziens!